Welcome to Visual Algebra Lecture 2.9, Semidirect Products Intuitively. In the previous lecture, we rewired the Cayley graph of the dihedral group to get new groups like the semidihedral and semi-abelian groups. What we were doing without realizing it was constructing a semidirect product of the cyclic group Cn with C2. In this lecture, we will explore this concept more generally by modifying a Cayley graph construction of a direct product. Loosely speaking, a semidirect product is a twisted direct product. Though we won't be able to fully formalize this until we learn about homomorphisms in Chapter 4, it will be advantageous for us to see this construction now. Additionally, many of our go-to examples of groups going forward will be semidirect products. We first saw direct products back in, I think it was lecture 2.4 on abelian groups, because every finite abelian group is a direct product of cyclic groups. I want to start this lecture with a review of that concept, and in particular of a visual construction of the Cayley graph of a direct product, because we can construct semidirect products by modifying this construction. Well, suppose we have two groups A and B with identity elements, column 1A and 1B. And suppose we have a Cayley graph of A with generators A1 up to AK, and a Cayley graph of B with generators B1 up to BL. We can create a Cayley graph for the direct product A cross B, where the vertex set is, of course, all ordered pairs of things in A and things in B, and then the generators can be taken to be ordered pairs of A generators with the identity element in B and the identity element in A with generators from B. Here are three examples: C3 cross C3, C3 cross C2, C2 cross C2 cross C2. This should not come as a surprise. Notice that these Cayley graphs have a boxy or grid-like shape because A arrows are independent of B arrows. I think you know what I mean by that. But algebraically, it means that the product of one of these generators from A and one of these generators from B can be done in either order. So A comma B is 1 comma B times A comma 1, or vice versa. It's important to note that just because a group is not written with the direct product symbol does not mean that there's not secretly a direct product structure lurking behind the scenes. For example, we have already seen that the Klein 4 group is isomorphic to C2 cross C2. Maybe that's not a surprise, but C6 is isomorphic to C3 cross C2. Sometimes it is even less obvious when there is such a direct product structure. For example, two of the following three groups secretly have a direct product structure, and it's probably not the two that you think. Meaning if I were to poll 1,000 random people who didn't know what direct product meant, they would probably get it wrong more often than if they had just randomly guessed, even if they were mathematicians who didn't know anything about algebra. Now, I'm not going to tell you the answer, but I will say that this is the dihedral group. You'll see this a lot in this course. This group will come up in Chapter 3 and Chapter 4. And by the end of Chapter 4, you will have enough knowledge to be able to answer this question. And I don't know if this one comes up in lecture at all, but it does come up in an old exam that's on my website from, I think, fall 2021. And also in my book in Chapter 2, I do eventually answer this question. Semidirect products are a more general construction than the direct product. They can be thought of as a twisted version of the direct product. To motivate this, consider the following inflation method for constructing the Cayley graph of a direct product. This is from Nathan Carter's Visual Group Theory book. Now, I'm not going to describe it in its full generality. I'm just going to do an example, and I think you should be able to extrapolate how this works for general groups. So I'm going to start with a copy of the group B, which is C2, and B is for balloon, because I want to take each node and inflate it like a balloon. And then inside of that balloon, stick a copy of the Cayley graph for the other factor, A, which in this case is C4. Now, when we do this, for any two balloons, we have twins of nodes. And if there's an edge connecting the two nodes in the original Cayley graph, then we're going to put an edge between each corresponding twin node in this inflated copy. And then we take a needle or pencil or something and just pop both of these balloons, and voila, we have our Cayley graph of the direct product C4 cross C2. Now to connect this to semidirect products, suppose we do the same process, but when we stick in the nodes in the bottom balloon, we reverse the red arrows. So they go this direction. You see what group we would get if we did that? You've seen this group before. It would result in a Cayley graph for the dihedral group D4. We say that D4 is the semidirect product of C4 and C2. I should probably say a semidirect product because sometimes there's multiple ways to do this. In this case, there's not. And we write that using the same notation as the direct product, but we just have an extra vertical bar on one side of that direct product symbol. So this is not a formal method. You should have a lot of questions. You should ask things like, what happens if you reverse the order? What if you stick copies of B inside of A? Is this symmetric? Answer is it's not. And there's a lot of other questions you could ask, and you should be asking. The idea for this is just sort of get those neurons firing and get some intuition. Reversing the red arrows in that last example worked because it was a structure-preserving rewiring of the Cayley graph. Formally, this is something called an automorphism, which is an isomorphism from a group to itself. We'll learn more about this when we study homomorphisms. For now, just know that it's a bijection from a group to itself, satisfying some extra properties. An automorphism modifies a Cayley graph, and there are two canonical ways to show how this is done. In one, we can fix the position of all the nodes and just rewire the edges accordingly. In the other, we fix the position of all the edges and we relabel the nodes accordingly. This is best seen with an example. So consider the cyclic group C4, which is generated by R, a 90-degree counterclockwise rotation. We could just as easily declare the generator to be a 90-degree counterclockwise rotation, and that amounts to just replacing R with R cubed. So we can do that by reversing these edges to get this Cayley graph here. Or we could fix the edges and just relabel the nodes accordingly. So swap the positions of R and R cubed. Now there are other ways to rewire this diagram, but they don't preserve the algebraic structure. For example, if we fix the nodes but make these red arrows like this, then now one goes to R squared, but R squared goes to R. That doesn't preserve the algebraic structure, so it is not a valid automorphism. I also want to mention that sometimes we call these two things phi rewirings and phi relabelings, respectively. As I mentioned earlier, semidirect products can be constructed via the inflation process for A cross B that we saw earlier, but we insert rewired copies of the Cayley graph for A into inflated nodes of B. Let's do an example right away. Let's construct a semidirect product of A and B for those same two groups that we saw earlier. A is the cyclic group C4 and B is C2. And we will use the rewiring phi from the previous slide that just reversed the red arrows. So we start with a copy of B, and here's a mnemonic: B for balloon and A for automorphism, which is a rewiring. I get these confused all the time, so I literally go back to this mnemonic and use it myself. So we start with a copy of B, and we inflate each node into balloons, and then we insert rewired versions of A into each node. And this node will put the identity rewiring, and this one will put the non-trivial rewiring. And then we connect up the corresponding twins of nodes because there's an edge between the original two nodes. And then as before, we pop each inflated node, and there we get the semidirect product of C4 and C2, which is isomorphic to D4. For now, I'm going to put a little subscript phi here, which is the rewiring, although I will change that convention by the end of this lecture and going forward. Notice that in the middle graph, each inflated node, there's two of them, is labeled with a rewiring. This one we say is the identity rewiring, and this one is the non-trivial rewiring that reverses the arrows. Formally, this labeling is a map whose input is C2. So we start with the two nodes of C2, and for each node, we output one of the rewirings. In this case, we put the identity map here and the non-identity rewiring down here. So here's a function that specifies which rewiring gets placed into which inflated node of C2. So going forward, I will replace this phi with a theta that describes this map, describes this labeling for every node. Now, there are strong restrictions for inserting rewirings of the Cayley graph of A into B. We can't just do it arbitrarily. The map theta must be a structure-preserving map called a homomorphism between groups. Now, that's the topic of chapter 4, so I won't define it here. But all you need to know in this chapter is that it satisfies the following condition. If we stick a phi rewiring into an inflated node B, then we have to stick a phi squared rewiring into the node B squared, and so forth. So we have to stick a phi cubed rewiring into the node B cubed, and so forth. So for example, if we do that previous example with, this is the identity rewiring, and this is the rewiring phi. Let me do it this way. Then suppose that we tried that same construction, but with C3. So we have, so here's C3, and here is node 1, here is node B, and here's B squared. So if we start with the identity rewiring here, which we're going to have to, as we'll see later. So this is phi to the 0, which is the identity. Then if we put the rewiring phi over here, phi to the first, then we have to put phi to the second over here, which is the identity rewiring. So that means we have to put the original rewiring here. But then phi cubed is up here, and so B cubed is up there, and because 1 is equal to B cubed, that means that we have to stick the rewiring phi cubed. So notice this is phi cubed, and this is phi squared, and phi to the 0. So that means we have to stick this rewiring in here, but now we have a contradiction because we have two different rewirings that have to go in here. So this homomorphism condition is going to prevent there from ever being a semidirect product between C4 and C3. Maybe I should write this as C3 for the balloons and then C4 here. Now, I said something technically wrong. I said there's no semidirect product here, and let me emphasize this. But there actually is one. There's a trivial one. There's one where there's the direct product, where you just stick the trivial rewiring in each of these nodes. So it's important to note that the standard direct product is technically a semidirect product, but we don't usually use this symbol unless it's not a standard direct product. So here is our informal definition of a semidirect product that really hinges on this visual picture of rewirings and balloons. and the inflation process. Consider groups A and B and a structure-preserving map, theta, from B to the set of rewirings of A, which I'm going to call aut of A, aut for automorphism, and this turns out that it's a group, though it's not clear at this point exactly what that means or why. The semidirect product of A with B, and I'm going to put the subscript theta to denote this map, is constructed as follows. We first inflate the nodes of the Cayley graph of B, think B for balloons, and then we insert rewirings or rewired copies of the Cayley graph of A into each node. And this labeling map tells us which rewiring we put into node B. And then for each edge between B nodes, we connect corresponding pairs of A nodes with that edge, and then we pop those balloons, and we're done. I think the trickiest part of this definition is this labeling map. So let me emphasize this. For groups A and B, this map theta goes from B to the rewirings of A, and it literally tells us which rewiring of A does node B get labeled with. So again, for each node of B, we say this is theta of 1. So if this is 1, this is B, and this is B squared. These labelings are telling us which rewiring, which is an element in here, we get to put inside this node. As I said earlier, any group A always has a trivial rewiring where we just don't do anything to the edges. And if we define the map theta to send every element to that trivial rewiring, the semidirect product construction that we just saw constructs the direct product. It's actually just that inflation method that we saw in the beginning of this lecture. Until we revisit this topic in Chapter 4, we will pretty much only see semidirect products involving cyclic groups. And that's because there's a very nice way to characterize the rewirings of a Cayley graph of a cyclic group. And before we do that, let me just mention that for any n, well, I should say n at least 3, there is a rewiring of the cyclic group that just reverses all of the R arrows. The semidirect product of Cn with C2 with respect to the following labeling map that sends the identity element to the identity rewiring, and it sticks this reversal rewiring in the non-identity node, is just Dn. So we say that Dn is a semidirect product of Cn and C2. So for example, I think I did, we can do this, let me do another example that we haven't seen yet. Here is D6, which can be constructed as with this inflation method where we reverse the edges in the bottom node. I've had several people ask me why I introduced semidirect products this early in my book and in this course, and I have some good reasons for it. First of all, it helps us understand a new way to construct groups, and this chapter is all about examples of groups. It helps us understand the structure of some groups we've already seen, like the dihedral group. Thinking about what works in this process and why helps us gain a more holistic understanding about group theory. I think that exercise about sticking in phi rewirings into B, forcing phi squared rewirings into B squared, is going to pay dividends later on. That's really the intuition of a homomorphism. Also, it will be easier to learn advanced concepts such as automorphisms if we get a preview of them in advance and gain intuition. Otherwise, it will feel like I'm pulling it out of left field. One thing that I want to mention here, we won't be able to prove it until chapter 4, but it should seem reasonable that the set of rewirings of a Cayley graph of G forms a group, denoted aught of G. What's less obvious is that this group does not depend on the Cayley graph, but it depends on the group itself. I want to finish this lecture with a few more examples of the automorphism group that we just defined. The one that we saw earlier of C4 just had 2 rewirings, so it was kind of boring. If we go up to C5, there are 4 rewirings, or 4 automorphisms of the Cayley graph generated by a single element. And as I mentioned earlier, that's a property of the group, not the Cayley graph. Here are those 4 rewirings. If we take this one to be our starting graph, then this one is achieved by replacing each copy of A with A squared. You can think of that in terms of the graph as replacing each red arrow with a double red arrow. So red now becomes the new generator. So the arrow from A goes from A to red. It goes to A down here, so forth. So I like to call this the doubling map. It just doubles the length of a red arrow. Now we can repeat this process. If we double a red arrow from here, so now starting from here, if we replace red with a single red arrow, we get an arrow from 1 to A to the 4th. And that gives us this rewired Cayley graph. Now if we double this map, we replace red with red, and we get this one right here. Notice that algebraically, again, we are doubling, which means squaring, because we're doing things exponentially. So replace A with replace A with A squared. And now over here, we're replacing each A squared we're squaring that to get A to the 4th. And then if we square it again, we get A to the 8, which mod 5 is A cubed. So I'm saying doubling, but I'm also saying squaring, because when I say doubling, I'm talking about the exponents. Notice that the rewirings form a group. So there are 4 rewirings, and there are 2 groups of order 4. So which one is this? Well, this doubling map here, if you do it twice, it's not the identity element. So it has order 4. So it has to be a cyclic group. So here is a Cayley graph of the automorphism group of C5. So this is the identity rewiring. This is the doubling map, the quadrupling map, and this is the tripling map up here. And I like to stick these things, rewirings, actually in the nodes. So you can see them like this. And in the next lecture, we will construct the semidirect product of C5. This is remember, A for the thing that gets rewired, automorphism, with C4 by sticking these things into these nodes and then connecting up these edges like what we did earlier in this lecture. So if I don't think I can do this very well here, but you can imagine what would happen if I connect these things up. We will do this, and I actually have graphics of it for the next lecture. And there's actually going to be several ways to do this. And in this construction, we will get multiple semidirect products of C5 with C4. But that's in the next lecture. I know I said this before, but I really want to emphasize it. For any group G, the set of rewirings forms a group called its automorphism group. As promised, we'll dive into the automorphism group of the cyclic group Cn. So I claim that each automorphism is defined by where it sends a generator. This time I'm going to use R instead of A. Now, I'm going to later name this automorphism. I'm going to call this sigma k. And you can think of it as the k-tupling map. So that word generalizes doubling, or I guess tripling, quadrupling, quintupling, sextupling, k-tupling. In terms of a Cayley graph, think of it as the map that replaces each red arrow by k red arrow. So it like multiplies the red arrow by k. The automorphism group of Cn, I claim, is isomorphic to a group that we haven't seen before. We'll call it UN. U stands for unit, and that's a term from ring theory that we'll see in chapter 8. But it consists of the numbers that are relatively prime to n that are between 1 and n minus 1. So 0 and n are never going to be co-prime to n. We're going to assume that n is like bigger than 1. Otherwise, this is pretty trivial. So it's a set of all k between 0 and n that are relatively prime. And the operation on this group is multiplication mod n. So even though we haven't actually seen this group, we've seen all finite abelian groups. So for C7, there are 6 numbers that are relatively prime to 7. And there's only one abelian group of order 6. So this has to be cyclic C6. So what's a generator? Well, we know what the Cayley graph of C6 will look like. It looks like, pardon my drawing, it may not be great here. So 1 will definitely be the identity, but then what's a generator? Well, there's going to be 2 possible generators. There's this one and that one. These are the 2 elements that have order 6. These elements will have order 3. This element has order 2. So if you notice, it's tempting to take 2 as like the generator, right? But 2 cubed is 8, which is 1 mod 7. So 2 does not have order 6, but 3 does. So 3 squared is 9, which is 2. And so that means that 3 cubed is 2 times 3, which is 6. And 6 is equal to -1. So at any time that we have 3 cubed some power equals -1, we can say that if we square that thing, we get 1. So this is going to have, 3 is going to have order 6. So if we put 3 here and we square 3, that's 2. And then we cube 3, that's a 6. Raise it to the 4th, we get 4. And we raise it to the 5th, we get 5. So here's a Cayley graph for UN. I should say for U7. Now, if we define this map up here, this k-tupling map, as sigma k, then a Cayley graph for the automorphism group C7 is going to look like this. Do you see? How about if I just write it down? So here's the Cayley graph. It's just, well, the elements are not the numbers 1 up to k, but they are, and I don't think I'm going to do this for the entire table, but think about why this is what we want. So if we double a red arrow and then we triple it, then the result is that we sextuple it. Or if we triple it and then we quadruple it, we've just multiplied it by a factor of 12, which is 5 mod 7. So so later in this class, we will say that there is an automorphism from, well, we can say now that UN is isomorphic. I said automorphism, I meant isomorphic. UN is isomorphic to the automorphism group of C7, and later we will formalize this by defining a map that sends K to the k-tupling automorphism up here. Since U7 is generated by 3, the rewirings of C7 are generated by the tripling map. So if we triple the red arrows, replace each red arrow with 1, 2, 3, that we get this one. And then we triple again, replace this with 1, 2, 3, that's the doubling map. We triple again, 1, 2, 3, that's the map, the sextupling map. Then we triple this thing, we get 1, 2, 3, that's whatever this is, the quadrupling map. And then we triple this again, we replace each red arrow with 1, 2, 3, that's the quintupling map. And then we do that again, replace this with 1, 2, 3. Now we're back to where we started. So here's a Cayley graph version of that, and here's the algebraic version. Notice that every time we're just tripling the previous. So we triple r to the first, we get r. We triple r cubed, we get r to the ninth, which is r squared mod 7, or the exponents are reduced mod 7. We triple it, and by tripling it I mean cubing it. We get r to the sixth, r to the fourth, r to the fifth. Finally, I like this picture a lot. Here is a Cayley graph. It's better than the hand-drawn one that I had in the previous slide, of the automorphism group of C7, where at each node I have put in the corresponding rewiring. So once again, if you triple these red edges, you get this. You triple that, you get this. You triple this, you get this one, the sextupling. You triple this, you get 1, 2, 3. You triple this one, you get 1, 2, 3. So you get 1, 2, 3. This one, and you triple that, you get back to where you started. Okay, so that's a good place to stop. Next time, I will revisit that example that I showed you, or that I touched upon briefly about C5, semidirect product C4. And I'll construct that using the inflation method, and we'll see that there are actually two non-abelian semidirect products. So there are two different non-trivial labeling maps, and they will give us two groups of order 20. And then I'll show you the Cayley graphs for both of those with the edges rewired and the nodes relabeled. And they'll look different. And because there's going to be two different colors of nodes, one of them will, how do I say this, rewire the red edges and fix the blue ones. And the other will, or I should say tangles the red edges and fixes the blue ones. And the other one will fix the red edges and tangle the blue ones. And then we'll finish by looking at semidirect products of C8 with C2. And we'll see that the groups that we've previously seen of order 16, like dihedral, semidihedral, and semiabelian, are all examples of semidirect products. And that's just going to be a really neat way to finish that lecture and this topic on semidirect products. So stay with us.